Okay, yeah, great. So this is actually preliminary work. Paper's not out. It's not even that close to out, but I think it's going to be different from what other people are talking about. So I wanted to talk about it anyway. And everything, well, the new math that's in here today is joint work with Vlad Bickel at Courant and Samir Iyer at UC Davis. Okay, so we're going to start with a phenomenon. We're going to start with meteorites. So when you have asteroids and they start entering Earth's atmosphere, they become meteorites. And you can find, apparently, you can find a lot of meteorites that have this conical shape. So as the idea is that as they enter the atmosphere, then they get eroded and then they form this conical shape, which seems to be stable. And then you find them. So the credit for this goes to Leif Ristroff, who's at the Applied Math Lab at Courant and who worked on a lot of the experiments related to this stuff. Okay, so you find these conical meteorites and you want to understand their formation better. So you set up an experiment in the lab. You take your water channel and you take a clay cylinder, you put it in the water channel, put a camera on top, and you let the thing run and you see what shapes it forms. And so when you do that, here's what it looks like. Clay cylinder. All right, so obviously, eventually the thing erodes away to nothing. Okay, what are we seeing here? We're seeing that we're just seeing the pole that the cylinder is stuck on. But as this thing erodes, so let's watch it again. Before it disappears, it seems to approach this, they call it this triangular or quasi-triangular shape, and then shrink and disappear. And so I have to say that as a person who's interested in fluids, I find this very interesting and compelling. And so then I think explain that. Okay, so here's the paper that the group at Courant wrote. So they did some numerical simulations and compared it with the results of the experiment. So here on the left, we're looking at the fluid the interface of the clay body that's eroding in a simulation. Here we're looking at it rescaled to unit size, and here we're looking at the experiment rescaled to unit size. And so qualitatively, there's this quasi-triangular shape, and it appears to have good comparison. Again, this is just a model. So, okay, so we're going to try to explain this mathematically. So we're going to have we're going to set this up with PDEs. We're going to set up a free boundary problem. So we parameterize the boundary of the clay. Well, first of all, we just look at the symmetric clay. So there's this invisible line here, and this whole thing is reflected across, let's say. And we parameterize the body by capital X of S. So X is a vector in R2. S is the arc length parameter. And so then at each point you get this local frame ES and EN, and we can also define curvature kappa. And we're going to actually look at infinite bodies, and the reason for this is because it's really hard to say anything mathematically rigorous about the wake behind a body.
And Alex, should we understand that it's really like cylindrically
we're under,
or are you doing a two-dimensional?
We're doing a two-dimensional, and this thing is extended into 3D. And so this on the right-hand side is clay, on the left-hand side is fluid.
Okay,
thanks. Yes.
I was troubled also because you break the symmetry. So
yeah, so this in this case we impose the symmetry and keep it the whole time. But in principle, right, the real flows could break it. Yeah. Okay, so then you just write down the PDE for the evolution of this free boundary. So it has the evolution in the vertical, or sorry, in the normal direction, which you want to pay, which is really the evolution. You also have some evolution in the horizontal boundary, and that's really just a reparameterization. This is the Lagrange multiplier to keep thing arc length parameterized. Okay, so the model needs to be closed by understanding what is this normal velocity, and for that we need an erosion law. So we define the shear stress or the skin friction on the boundary by this tau. So it's the normal derivative of the velocity field running parallel to the boundary. And there's an empirical erosion law, but we lack a first principles derivation of it. So I'm actually going to propose a few laws, and it'd be very interesting to give a physical derivation of say the first law, which people are using. So the first candidate is that the normal velocity is proportional to the magnitude of the shear stress. And the issue with this law is that if you start with an initially smooth body, the law itself is not smooth, and you don't expect the body to stay smooth. So instead, you can work with this regularized law. So you take some function f reg, it's a regularization of absolute value. You can expect that smooth bodies at least have a chance of staying smooth. There's also this third law, which builds in another physical effect called the Gibbs-Thompson effect, which has to do with the curvature of the body. And this is the law that was used in the numerical simulations, or this is roughly the law that was used in the numerical simulations a couple of slides ago. And but we're going to be focusing on laws 2 and 3. So you have an erosion law, which lets you take a flow and calculate how the body should be eroding. So how does one calculate the flow? So we describe the flow by a boundary layer. And so what's the deal with that? Basically, in 1904, Parental hypothesized that at moderate to high Reynolds numbers, in a neighborhood of a solid boundary, you can have a reduced description of the flow in terms of a boundary layer. So if nu is the viscosity, or basically inverse Reynolds number, so nu, you can imagine nu is very small. So the boundary layer has thickness root nu, so it's also very small. And there's a reduced set of equations that you can solve to describe the flow there, called the steady parental equations. So this is roughly the shape of the boundary layer. And so we're going to use this kind of description. And for the law, we're using something called a quasi-steady formulation, which means that the idea is that at each time step, at each time step the body might be changing, but the fluid flow reaches equilibrium at a much faster time scale. And so essentially at every time you take the body and you calculate a flow from it, and that flow is steady. It responds instantaneously to the change in the body.
So the body is assumed to be convex?
Yes.
And it will stay convex?
Good question. I'll mention that. Very good question. That's very important to this. So just mention a quick thing. This is more for PDE people, but you can take that kind of perhaps cumbersome free boundary formulation several slides ago. You can write it in terms of the tangent angle at each point, and you get a much nicer looking scalar PDE essentially. And you'll actually see that the Gibbs-Thompson effect is popping out here. This curvature term gives you a dissipation. So here we have this funny PDE. It's in some ways it's like some kind of conservation law with non-local flux. This guy, but in any case, so you can work with this formulation. Now, what's one reason why we like this model? Because it actually has a family of exact traveling solutions. These 90-degree corners are exact solutions, and they just travel with constant speed. If you add in the Gibbs-Thompson effect, then we expect that there's also an analogous solution, which is just slightly smooth, but which is traveling with some constant speed. And one way you can show this is using so the flow is calculated using the boundary layer. There are these special solutions of the boundary layer equations that correspond to corners. They're called the Faulkner-Sconce solutions. And they're self-similar. And you can use the fact that they're self-similar to show that their shear stress is constant. So at every point on the boundary, this solution erodes the same amount. So it stays a corner, but it just moves backward. Okay, so this part is a slightly more for the non-PDE people in the audience. We're going to enter for a second into the mind of PDE people. What do PDE people worry about? And a fluid dynamicist once also called this the estimate community. So we start with this phenomenon that we want to capture mathematically. So we want to understand dynamics. What do the solutions do? So the conjecture would be that this 90-degree wedge, this exact traveling solution, is asymptotically stable. One might also conjecture that for positive epsilon, you add in this curvature effect, then there's also another traveling solution, and it's also asymptotically stable. So that's what you're really after. But so I wrote this as step 1. There's a step 0. The step 0 is really, do the equations make sense? So we talk about, are they well posed? Do solutions exist? Are they unique? Do they depend in a sensible way on the initial data? And so for most PDEs, you don't have to worry about that because they fall into a theory that's well developed, and we know that well posedness is kind of for free. This PDE is not so simple, and we expect that at least the viscous version is locally well posed. I have some expectation for the inviscid version as well, or rather for the version where epsilon 0. But yeah, for this model, well posedness is not straightforward, and you need to understand each operator in the PDE very quantitatively. So let's break down how you calculate the erosion model. So your first thing you need to do is calculate the flow. And when you calculate boundary layer flows, they're matched to what's called an outer flow. So you imagine very far away from the boundary, there's one flow, and near the boundary there's another flow, and they're coupled. Actually, it's like the outer flow forces the inner flow. So you can do this. So you say that U comes from a stream function, and you can solve the Dirichlet problem for the stream function. The flow is going to be irrotational, and there's some boundary condition at infinity. And from this, you can get what's called the Euler trace. And this step is somewhat familiar from water waves theory. When you do the Dirichlet normal map, there's a derivative loss. So then once you have this outer Euler flow, it enters as a forcing into the boundary layer flow. And so here are the steady parental equations. This capital U is the outer Euler flow. And as you see, it's a forcing term. And these equations can have blow up, actually. And you don't want that. So you want something called advantageous pressure gradient so that the solutions don't blow up. And this brings us to the requirement on the body, which has to do with convexity. So the second thing, I'll finish in 1 minute. The second thing about the parental equations is that they're actually, so they're called the steady parental equations, but they're actually an evolution equation, not in time, but they're an evolution equation downstream. So in other words, if you have some body and you start at the tip and you understand the knowledge of the boundary layer at the tip, you can understand it downstream by evolving. And basically there's a change of variables, which shows it very explicitly. If you change variables using von Mises transformation, you get this heat-like PDE, but it's quasi-linear because there's this U in front of the diffusion. And U degenerates near the boundary, so it's degenerate parabolic. And so, okay, once you do all this boundary layer stuff, then you can compute the shear stress, plug it back into the PDE, you close the system, and you try to say something about well posedness. One ingredient I want to highlight is that right. So we have this 90-degree corner, and you want to understand that you have an initial body which very far away looks like a 90-degree corner, and you want to say that it continues to look like a 90-degree corner. Basically, that the boundary condition is kept at infinity. And for that, you need to understand very well the downstream asymptotics of these parental layers. And so to do that, you revisit a beautiful theorem of James Sarin from 1967, which characterized the downstream behavior in terms of these Faulkner-Schaum profiles. In any case, that's one of our key ingredients. That's all. What's that?
In the three-dimensional case you gave it before, do you expect stability of the end of a cube?
I think if you take this picture and make it actually symmetric in 3D, I believe we expect it stable. but the 2D is already hard.
You mean rotationally symmetric?
Yeah, actually, so yeah, symmetric around this axis, so it'd be like it'd be a cone.
Because the picture was more like a triangle with something sticking out of it.
So like this?
Yes.
Yeah, I think we expected this a shape like this is
So it
It's
would be
stable.
like a cone.
like a cone, yeah, like a cone, yeah.
And with 90 degrees.
I believe so, but I haven't done all the computations in 3D because 2D was already challenging.
So should we understand your two-dimensional model as like, being infinite in like
In the
direction, which is like,
yeah, you should.
okay. So you're studying like, an infinite meteorite, which hopefully is not going to fall on the,
Yeah,
on the Earth.
yeah.
That is what your model is actually about.
Yeah, so the Orton experiment, it's a clay cylinder, but yeah, it's translation invariant in Z. That's right.
No, it's really it's relevant to meteorite because there is heat for meteorite. It's air and not.
Yeah, just the erosion is just caused by the intense drag on the surface. Yeah.
Maybe it's just my eyes tricking me, but it looks like in maybe the next slide of the simulation, I guess this like the shape kind of switches directions a little bit. And I guess with an infinite,
You mean like this guy or?
no, like it curves back inward towards the axis, like on the far right side of the object, like there's this little peak.
Yeah, you're saying that this is like a cone?
Yeah,
Yeah.
on the top.
Yeah, I took this from Life Ristroff, and yeah, that picture may be from a different experiment. Don't look too closely at that one, Matt. Okay, yeah, we should leave some time for the next speaker. So.
All right, let's take the speaker again.